Welcome. I'm Lisa Blackburn. This is my YouTube channel, and today we're in AP Chem talking about equilibrium. Okay, where did I do with my paper of it? It's over here. I had something wrong. Dami figured it out. I had put a decimal point in the wrong place. I had to go back and check it. Okay, so here we got two people pulling on a rope. But do you think this is, don't look at the answer, static or dynamic? They're just sitting there, nothing's moving. And if y'all remember, if you've had physics, static means nothing's moving. So there's no movement, that's static equilibrium. That's not what we're talking about in this chapter of equilibrium. We're talking about chemical equilibrium, and it's dynamic, which means, like here I've got ethanol in an empty flask, and when you let the ethanol in, and you have ethanol that's in the liquid, and then you also have particles that have become a gas, and it's an equal rate. Just as many particles are evaporating and becoming gas as ones running into each other, running into the sides of the container, and going back into liquid. So the amounts are staying the same, but the molecules themselves are moving. It's at the two processes are going on at the same rate. So that's what we're talking about in these chemical reactions. It's a dynamic equilibrium. So here's another example of it. You have a saturated, supersaturated, well, it's just saturated, but there's extra salt in the bottom of salt and water, that you would have equal amounts of salt that is dissolving and going into the water to be ions. At the same rate, you have other salt joining onto this crystal and going back and recrystallizing at the same rate. So chemical equilibrium is when the forward and the reverse reactions proceed at equal rates. I should say equal, not equals rates, equal rates. So how we represent that is by the double arrow. So the obvious thing that this reaction is at equilibrium or that it's reversible is it got the double arrow. It can go both ways. Okay, so in your book, there are some pictures of an equilibrium where it's got these two chemicals. It starts off with this chemical and it's colorless in a test tube, but then it decomposes into this chemical, which is brown. So when you look at the little pictures, it starts off clear and then it gets brown, but it doesn't mean that all of this turned into that. It means that some of it got turned into it and some of it's turning back into colorless. So it's not as dark brown as it would be if it was all that. So this was the reaction in your book, and it starts off with just the clear stuff, but then after a while it starts turning brown, so we know that the nitrogen dioxide is there. And our question was, at some point, the color of the tube starts changing. The student decides that the reason why it stopped changing is because the reaction is over and all of the N2O4 have become NO2. And this is wrong. It's going back and forth. It's a reversible reaction. It's at this dynamic equilibrium. So this is the definition of equilibrium. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. They're happening at the same speed, same amounts. Same amounts are happening. And once equilibrium has been established for a chemical reaction in a closed system, the concentration of the reactants and products no longer change with time. Now, some of the reactants are becoming products and some of the products are becoming reactants, but it's not changing anymore. See, you learned all that in honors, didn't you? Just easy review. Some of the reactants are constantly being converted to products and vice versa, but the concentrations are not changing anymore. Oh, I want to erase this. Let's see if y'all can know these. All right. So let's see if y'all know, if y'all can answer these true or false questions. Get my pen. All right. Once equilibrium is established, the concentration of A is equal to the concentration of B. Do you think that's true or false?
True.
False. Very good. And we don't know if they're equal. It could be an equilibrium where almost everything goes to be a product, or it could be an equilibrium where just a little bit goes to be a product. These are not going to necessarily be the same, but the concentration of A is not changing anymore, and the concentration of B is not changing anymore. We don't know which one's more. They could be equal, but they could not be. Once equilibrium is established, the rate, Kf, is the rate of the forward reaction for A is equal to the rate of the reverse reaction for B. True or false?
True.
True, yes. That's what's true. Okay? Once equilibrium is established, the values of the concentration of A and B are no longer changing.
False.
True.
False.
True. Now, some of the molecules are changing, but the concentration stays the same. As many are becoming products or as becoming reactants. Once equilibrium established, A and B are no longer reacting. False. It's just at the same rate. The concentrations are staying the same. Okay, once equilibrium is established, the ratio of B divided by A equals 1. False. Once equilibrium is established, the ratio of B divided by A is a constant. True. Yes, there you go. That's the truth. So, okay, and the next thing is we're going to draw a little line. So here we have two experiments, and we're supposed to draw a line where equilibrium was established. And where it is, it's where the lines get flat. Where the lines get flat, the concentration isn't changing anymore. So with this experiment, we started off with H2 and N2, and we didn't have any NH3. So we only started with reactants, but over time, the amounts of all three leveled off. With this one, we started with the no hydrogen and no nitrogen. We just started off with the ammonia, but with time, they leveled off. And notice they leveled off in the same order, too, for their concentration. And notice they're not all the same, and they don't equal 1. Okay? All right. So both experiments end up with all three chemicals at the same concentration at equilibrium. Experiment 1 began with only reactants. Experiment 2 began with only products. Once it was achieved, were those three concentrations the same? Nope. See, they're on different levels? No. Okay, so this is the formula. When I taught it to you, I said A plus B equals C plus D. They don't use C, and it's because they put a C here, and I'll explain it to you. If you'll look for a second. Okay, when I taught this to you, I called K sub C Keq. But really, Keq is an umbrella term. This stands for K sub C when you use concentrations, and K sub P when you do the same exact thing with pressures. So they call this K sub C because it's concentrations, and they don't use C as one of their reactants or products. Does that make sense to you?
So
Why it's a little bit different?
is it K sub P if it's pressure?
It's called K sub P.
Alright.
And all of these have the same exact formula, that, including Q, if you remember. It was the same exact formula. There's one reason that makes this pretty easy. Okay, so this is an example. Here's a reaction. They're all gases. You write the products in the numerator raised to the power of their coefficient. You write the reactants in the denominator, the concentration of the reactants, raised to its coefficient. And sometimes they just make you write the expression, and sometimes they tell you what the concentrations are, and you have to fill them in and do the math. Y'all remember that from honors? Doing that? Okay, so here's another one. This one, here are the products. They're written in the numerator. They don't have coefficients, so they don't get a power. They're, well, 1, but you don't write it. That's the reactants. It goes in the denominator, raised to the second power. So I think they're really easy when they don't make you use any numbers and you just have to write the expression. I always like that one. Now, don't get this confused with what you're doing on the test tomorrow. On the test tomorrow, is what we're talking about is kinetics. We're talking about the rate, and you only look at the products, the reactants. The products have nothing to do with it. Y'all remember that? So don't let this confuse you. The one is having to do with equilibrium. The other one has to do with reaction rate. All right, so they wanted us to take a little look at how these concentrations changed in different experiments. So this one started off at 10, and then it was 9.3, so that was 0.7 was our change. Here this started off with 0, and then our final concentration was 1.4, so it was plus 1.4. So this is how you write it. If it's getting less, you write it as minus. If it's getting more, you write it as plus. So we have several examples of this, and it's just finding the difference between the first line and the third line and writing it down. So y'all can fill those out quickly, and then we're going to look at them. Everybody see where I got that from? Okay, now let's look at them. What is the relationship between 0.7 and 1.4? What's the relationship between 4.51 and 9.02? What's the relationship between 1.9 and 3.8? And what's the relationship between 1.72 and 3.44? Double. So notice the stoichiometry, one of these to two of those. So we can see that there is a ratio, there's a relationship. Oh, and there's our other one, 0.22 and 0.44. Now, I didn't talk about whether or not it was positive or negative, but the absolute value was 2 to 1, and it was because of the coefficients. There was a relationship where that one is half of that one. Okay, so we're going to see that there are relationships in these concentrations, and their change in concentration that is reflected in our math. Okay, so we were supposed to write this, K sub C, our equilibrium expression, and so we put products on top, reactants on bottom, raise it to the power. Now, we're going to fill in these concentrations. So here we take our 1.4, put it in the numerator, square it, divided by 9.30, and the answer is 0.21. We do our second one, same thing, 0.98 squared divided by 4.51, oh, it's 0.21 again. And in fact, they're all 0.21. So you can see that this is a constant no matter what the concentrations at equilibrium is reflected in this constant number for math, this ratio. That we could put different concentrations in according to the stoichiometry. We're going to get the same reaction of constant.
Is it constant because like just for this equation, or like?
It's always going to be constant. Okay. So this is just showing you mathematically where these numbers came from. So explain the difference between Kc and Kp. Okay, Kc uses the concentration values in molarity. Kp uses partial pressures in atmospheres, but the formula is the same. It's products over reactants raised to the coefficient. Under what conditions would they be the same? And it would be if the change in the number of moles is 0. It's got the same number of moles on each side. Then they are the same. You can solve one from the other with this equation. They're related. You can take the concentration times the constant R, same one we used in our gas laws, times the temperature times the change in number of moles. The change in number of moles is the moles of product minus moles of reactant. And do these things normally have units? No, which makes them a little bit easier. Another reason why this is a little bit easier. How are we feeling about these concepts so far? Okay. All right, moving right along. Okay. So before they teach you about K being greater than or less than Q, they wanted to just think you to know this general trend. If K is big, way bigger than 1, that means that equilibrium lies to the right, and we say that as products favored. So if it's big, the reaction goes more toward completion. If it's real small, it goes more toward the reactants. It doesn't go very far toward completion. Okay, just to kind of get that in your head. So here are some examples. Here you've got the equilibrium expression. We put products over reactants, raised it to the coefficient, and its Kc was 0.21. We saw that on that other page. But if you look at it reversed, it's not the same Kc anymore. And it's not the same constant. Instead, you take the reciprocal. So if it reverses, you need to know that then, of course, these are reversed, and your number is going to be different. So reversing it does cause you to have the reciprocal instead of the thing. Okay? Feeling good about this? Good so far? And that's why I put the turtle upside down. He's a reciprocal turtle. There wasn't a whole lot to draw for this. So I just gave you some little animals to try to illustrate the concepts. So that's the reciprocal. So here we see the one above doesn't favor the products or the reactants. So Kc is greater than 1 because 47 is bigger than 1. So that means it favors the products. When it's big, it goes more toward completion. Okay? Feeling good about this still? Okay, and if we reversed it, then it's the reciprocal, and that's less than 1, and it would go toward the reactants. Okay, the next thing, I don't see why you would want to do it, and I don't really remember doing this when I've studied this before. So this might not be super important on the AP exam, but we should still pay attention and learn it. It's not hard, but it's just something that I've never really seen done much before, okay? So let me explain to you what it is. It's this next page. I thought about skipping this page. Okay. So here we've got that information from before. There it is forward, there it is the reciprocal. But what it's saying here is that you can take an equation and you can multiply it. Do you see how this equation is not the lowest coefficients? It's been multiplied by 2. And if you multiply an equation by a number, then it will change your K to that power that you multiplied it by. Okay? So just file this away in your knowledge bank somewhere. I don't know why you would ever want to multiply it and have an incorrect equation, but if you do, you raise it to the power that you multiplied it by. That's the first thing they do to it. Second, they did it some more. Here they multiplied it by 1/2. So they took it to the power of 1/2, which is the same thing as square root. Everybody remember that from math class? Raising something to the power of 1/2. Your calculator will do it either way. You can raise it to 0.5 or take the square root. It'll give you the same answer. Or this one, notice they multiply it by 3, so they took it to the 3rd power. Okay? Don't know why anybody would want to do that, but they don't stop there. They said you could also take some reactions and add them together. So this is a little bit like when we did Hess's law. So if things are on both sides of the reaction, you mark them out. So so they added these together, and when they did, BR2 was on both sides, so they marked them out before they added them together. Do you see that? So when you do that, you multiply the KC's, the equilibrium constant. So if you add reactions together, you can multiply the KC's to get the new KC. And I'll try to find out when we do the I do, we do's, and when we do we're going to do some AP practice test. Y'all keep just sort of look and see if there's any problems on this, because if there's not, it's probably not on the AP test. But if it is, it is. I just don't remember doing that in college chemistry at all. And I tutor college chemistry. Like, I've never stopped tutoring college chemistry since I got out of college, so I've been doing it for years. And I don't remember tutoring that either. But maybe it's a thing. So anyway, what you do to these is it's the product. That means multiply. That's fancy math for multiply. Okay, so here's one where they did this. They wanted to add these up. But to do it, they wanted to mark stuff out. And so they took the first one and multiplied it by 3. So that means they took their 54 and they're going to need to do it to the third power. Remember that? And then they flipped this because they wanted to mark out these 3 H2s. So this one, they're going to have to take its reciprocal. Everybody followed that? So they added them together, and then they took the new KPs, they took that one to the third power times, remember we multiply them, the reciprocal, and got that. Got our new KC for that reaction. It's a fun problem. I don't hate on it. It's fine. I don't see any reason to do it. But maybe there's a reason. I'm not a research chemist. I don't know. Maybe that's important in the world of real chemistry. I should ask Nathan. He's in the world of real chemistry. Do you ever do this? He's doing organic chemistry, though. He's probably not doing this. All right, can we go on down? Going on to 15.4, heterogeneous equilibria. Okay, what happens when we have a chemical reaction that involves a pure solid or a pure liquid? You already know this from honors. We don't include it. So you don't include solid or liquid. You do include gas and aqueous. So if it's solid or liquid, you mark it out. So if we were going to get the Kc for this, it would be CO2. If you were given partial pressures, Kp would be P of CO2. So I always like that. I like it when I get to mark stuff out and not have to do math on it. I've always thought it was fun. I like it in algebra when the same thing is in the numerator and denominator and you get to cross them out. Love those problems. It's just fun. Marking out math is fun. So I like this. The pressure of CO2 is at certain temperatures is the same, whether there's a pure solid there or not. That solid's not going to be having an effect on anything. So here are a few to do. Now, you can look at my first one. Then I want you to do it yourself. Then look up and see if you got it right. So in this one, number 1, I marked out the water because it's a pure liquid. I put the products on top, CO. I put the reactants on bottom. There it is. Okay, so now you try to do them by yourself and then look up and see if you got them right. Because I think this is easy, and you're going to remember this from honor, so give it a try. Yes, Z.
Is this pretty much what the test is going to be, the next test?
The next is going to be part of it, yes. It's going to be this, and then we're going to talk about pH. Remember, pH is easy. You get to do those negative logarithms. It's always fun when you get to use the fancy buttons on your calculator. And then we're going to kind of combine pH and this. And these are considered big ideas in AP Chem. There will definitely be some free response on this and on the pH and on what we just did, the kinetics. Those are like 3 guaranteed problems that'll be multi-part. And you know what they are going into them. So I think you're good. I think I'm starting to feel real good about where y'all are knowledge-wise. We've almost done it. We've only got one last thing, which has to do with more about heat. We'll go back to heat a little bit at the end after this. But we've almost learned it all. And this one right here is a lot of it you already learned in honors. Okay, did y'all get them right? So for number 2, you mark out the solids. So products on top, reactants on bottom, both of the second power. Mark out the solids on that one. Even though these are ions, we still write their little concentrations there. Raise them to the power of their coefficient. That one's got a pure liquid. Mark it out. Put products on top, reactants on bottom. And this is what I told you, that Keq is an umbrella term that includes Kp and Kc. And when I've seen in other books that they'll just use Keq instead of Kc. So just know if you see Keq, Kc, Kp, they're all really pretty much the same thing, same formula. They're your equilibrium constant. Can I move on up, or you need it back down some? Nope, you're good. Anybody else need it? Okay, I think y'all are doing great so far. 15.5. Okay, now, sometimes you're given concentrations. What do? You substitute it in and do the math. We did this in honors. Now, this is our new thing. This is the thing you haven't learned yet. It's called an ice chart, an ice box, a rice chart, or a rice box. I like the rice chart because I like to use a reaction as a table, and that's what you do. Okay, so what does ice stand for? Ice, I is your initial concentration. C is how much did it change, how did it change, and E is what is it at equilibrium. So, oops. Okay. So, here I have a reaction, and we're going to make a rice chart for it. Okay, which means you just write your reaction first. That's the R. So sulfur trioxide gas decomposes at a high temperature in a sealed container to produce sulfur dioxide and oxygen gas. This is a reaction at equilibrium system. Initially, the vessel is charged at 1,000 degrees Kelvin with SO3 gas at a pressure of 0.5 atmospheres. So it starts off there. The total pressure of the reaction vessel at equilibrium is 0.65 atmospheres. Make a rice box to help you calculate the pressure of all 3 gases at the vessel at equilibrium. So what you did in honors is sometimes I gave you the concentrations and you had to calculate what Q was or what K was. What we're going to do different is we might not know all the concentrations, but we'll know enough that if we use algebra, we can figure them all out. Okay? So let's look at how this works. Okay, so we started off, there's our reaction. Initially, we had 0.5 atmospheres of this, and we had none of that. But then, this is going to decrease as we make that, and we look at the stoichiometry to know how much. This is going to go down by 2x. This goes up by 2x. And because that's a 1, that one's going to go up by x. Everybody good so far? Okay. Then we add these up. So 0.5 minus 2x, we write that down. 0 plus 2x, we write that down. And 0 plus x, we write that down. Now, don't write down this yet because we don't know that yet. That's the answer, and we can't figure that out yet. What we can do is look at what we know. And what we know is we can do this math. And we can, if we do this math, 2x, negative 2x plus 2x, those cancel out, don't they? So what we're left with is 0.5 plus x, and we know the answer that these added together is 0.65 atmospheres. Now we can use algebra, we can solve for x, we can plug it into these values, and we get the answer. So, to get x by itself, we subtract 0.5 from both sides, and x equals 0.15. So we go back over here, and we do 0.5 minus 2 times 0.15 equals 0.2. 2 times 0.15 equals 0.3. And 0.15 just filled in as 0.15. So I like to box the x when I get it, and then I like to box the answers when I get them. And then this is going to be a multi-step question on the AP exam. So they're gonna want your rice chart, and then they're gonna want you to take these answers and do something with it. So what they wanted you to do next is saying, okay, well now you've got your concentrations. What's the Kp? So we can fill them back into our expression, and we can get the Kp is 0.34. You see, that's a nice little multi-step problem you can do, isn't it? Not too hard. Now, we're going to look at a lot of examples of it. And that's the basic problem there. You ready to go on to the next page? Another minute? Okay. I had to break our notes up into 2 things. All right. All right, I'll leave that there. Okay, so now we're on 5.6. So we are going to look at these positions and decide which way the reaction would go, but then we're going to learn how to use Q to do it the real way. It's like when in algebra you start off to solve systems of linear equations, you graph it, and then you learn how to do substitution, and you learn how to do the other one where you add them up, whatever you call that, add the reactions up, and then, you know, and you can get a better answer, but then you go back and learn how to graph them again on your calculator. So we're just sort of looking at it sort of from afar right now. This isn't how we'll really do it. But we can see that when we started this reaction, we had our initial gas here was at 1 atmosphere, and these were at 0 because we're just starting. So which way would the reaction go if you're starting with some of this and none of that? It's going to go this way, right? It's going to go right. It's going to go toward the products. What if we had a bunch of products and no reactants? We started on this side. Which way is it going to go? Left. It's going to go left. But here they both have atmospheres. We don't know which way it's going to go. And so we're going to have to figure it out. We're given concentrations, and we want to know, is it going left or right? What do? Q. Q to the rescue, okay? It's called the reaction quotient. And notice it is the same exact formula. If A plus B makes C plus D, you put your products in the numerator, the reactants in the denominator. So what's the difference? It's not at equilibrium. We don't know if it's at equilibrium or not, and we're going to do this problem and find out. Is it going left? Is it going right? Is it at equilibrium? Okay? So if these are all 1, we can fill it into our equation. We can put, our reactants on top, products on bottom, raised to the power of their coefficient, and they're all 1, so we could do this one in our head, couldn't we? What's 1 squared times 1 divided by 1? 1, right? So that's 1. So now we know our Kp is equal to 0.338. So we write them down, and always write your Ks before your Qs, and you can see which way it's going to go. So here's our greater than, less than, and it's going to make an arrow showing us which way it's going to go if you always write your Ks before Qs. So these notes originally didn't have that. I don't know if your book has it or not. I haven't looked yet. But always write Ks before Qs, and your greater than, less than will give you an arrow to tell you which way the direction's going. So 0.33 is less than 1. Now, do y'all like the alligator or Pac-Man? I like Pac-Man now. I used to like the alligator for the greater, less than, but now I like Pac-Man because it's easier to draw. Pac-Man wants to eat the 1, so the arrow's going this way, so our reaction would go to the left, and we know that now, and we can fill it in. But how we know that is because we did that problem. Do you remember doing that in honors? Everybody remember that problem we already learned how to do? Read our worksheet on honors. Okay, so if K equals Q, it's at equilibrium. If K is greater than Q, it's going to the right toward the products. If K is less than Q, it's going to the left toward the reactants. Okay. So here's a little practice for that. Here we can, for each one of these, we could fill it into our equation and get QP. Let me go back up and show you. We're putting it back into this, squaring it times the other one divided by the reactant squared. And this is what you get when you do that with these different numbers. Here it's 4, here it's 1.25, here it's 0.338. And we can write down our K's first, 0.338, write down our Q's, do greater than, less than, and we can know which way it's going. 4 is bigger than 0.338, so it's going left. 0.338 is bigger than 0.125, so it's going right. And here they're equal, so it's at equilibrium, there's no change. Don't know, I must have touched it. Okay, you ready for page 12? You feel good about that? You can do that problem if you had to. You remember doing it for honors? Okay, so I'm going to show you a bunch of rice charts and how to do them. Okay, so here's just one where they want us to calculate case C. Our equation is hydrogen gas plus iodine gas makes 2HI. And we're told we got our case C already, and we are given concentrations of 2 of them, but 1 of them we don't know. But we can set up this equation, fill in what we do know, that's the case C, and solve for X. So we can multiply 50.5 times 0.575 and 0.375, and then take the square root of both sides. Remember how to do that? And we can get the answer of the concentration. The one we don't know is 3.3. So that's a little fancier than what you had to do, than what my kids had to do in honors. I don't know about Corn. She might have had y'all do something a little more fancy like that. I did not. Okay, but that makes sense, right? We good so far? Okay, I think I'm going to erase the next one, and you can watch me do it. Let you see it step by step more. Okay, scroll up. Okay, so here is a problem that you would get on the AP test. We're still red. Okay, so hydrogen gas and iodine vapor were added to a previously evacuated flask. The initial concentration of each gas was equal to 2. The system was allowed to reach equilibrium. Calculate the concentration of all 3 species present at equilibrium. So you would have to first write your reaction and then balance it. And then you write down what you know to start with. And these both had 2 molar, and this had 0 molar. And then according to the stoichiometry, you know, we're starting with 2 here and nothing there, so we know it's going this way. These are going to go down by x, and that's going to go up by 2x. Everybody good so far? Okay, and then we can add these up, 2 minus x, 2 minus x, and 2x. Now we can fill it into our equation and solve for x, because we know the case C. We can put our products on top, which is the 2x raised to its coefficient squared. And then the reason why this is squared is just because I have 2 of them. Do you see that? I have 2 of these raised to the first power, so that's squared. Now to solve this, what should I do? I got 2 things that are squared, so how can I do that? I'm going to take the square root of both sides, right? Everybody agree to that? So that equals 7.11 equals 2x over 2 minus x. Now I'm going to go up here to finish my algebra because I have enough room. So now I multiply both sides by 2 minus x. Everybody agree to that? So it's going to be 7.11 times 2 minus x equals 2x. And now I use the distributive property. 14.22 minus 7.11x equals 2x. Now I gather up my x's and I get 14.22 equals 9.11x. Now I divide both sides by 9.11 and x equals 1.56. When I get x, I put a little square around it because that's my first thing. That's not the answer, but I'm well on my way to the answer. So now I take this, I fill it in here, and I can get the answer. 2 minus 1.56 equals 0.44 moles molarity. Put a box around it. That's the answer. Same. This is the same, so it's the same answer. And then I fill it in. 1.56 times 1.56 is 3.12. Put a box around it. And that's the answer to the problem. How do we feel about that one? Do you see yourself doing that on an AP test in May? Okay. Can I scroll on to the next one? Okay, so here hydrogen iodine gas was added to a previously evacuated flask. The initial concentration was 2. There was none of these. There's 2 of that. It was allowed to reach equilibrium. And so we're going to figure it out. So this goes down. We started here. This one's going down minus 2x. These are each going up by x because, see, those are 1s and that's a 2. We add them up, x, and 2 minus 2x. Now we fill it into our equation. So there's our equation. Okay, and then we've got it here. We take the square root of both sides, and we get 7.11 equals 2 minus 2x over x. We multiply both sides by x and get 7.11x equals 2 minus 2x. We add 2x to both sides and get 9.11x equals 2. Divide by 9.11, you get 0.22. Then go back over here and fill it in, and you've got the amounts. The only thing a little bit challenging is the algebra. And y'all are all pretty good in math, or you wouldn't be in here. Do you like it? I like these problems. They're big and fancy, but they're pretty easy. Do you like it, Philip? Is that what you're telling Katie? So I love these problems. These are great. Okay, let's look at another one. Let me explain it before you write anything down, because you can see it gets a little crazy here. Okay, so here's another one. All three gases were added to our previously evacuated flask, same equation. The initial concentration were each 2. The system was allowed to reach equilibrium. What is the concentration of each one present at equilibrium? So we know they started off at 2. These are going to change minus x. That one's going to change by plus 2x. We add them up. 2 minus x, 2 minus x, 2 plus 2x, okay? Then we can, first, we can figure out what Kc equals, because QC is what it is to start with. We're going to figure out what it is, and we're going to then figure out what it is at equilibrium. So filling this in, 2 squared over 2 times 2 is 1. Everybody see that? Then, and really you can't know this yet. I kind of got ahead of myself. So QC is 1. KC was 50.5. We do our greater than, less than. And KC is bigger than Q, so it's going this way. So we know that this is positive and those are negative. You didn't know those were positive and negative until you look at this. Do you follow that? I got ahead of myself and I wrote those positives and negatives there. Okay, so now I know this. I know it's going to go to the right, and I can put those there. And now I can fill it into my expression that I know, and I can solve for x. So I got my at equilibrium 50.5, my Kc. I've got it's going, I've got my products on top, my reactants on bottom. I solve it, and it is x equals 1.34. And then I go back and put it in, and I get the concentrations at equilibrium, 0.66, 0.66, and 4.68. Okay? Everybody understand? You got to compare your QC and your KC first to know if these are positive or negative. Which way is it going? Okay. Give y'all a minute to write that down, and then we're going to talk about Le Chatelier and his principle. Well, we're almost done. Just a little Le Chatelier, and we got it. Okay, you ready to move on? I see a couple writing still. Give y'all another minute. I know it's messy. It's hard to read when it's messy. Okay now? All right. So what is Le Chatelier's principle? We have a little illustration of it, that as pressure increased, yield increased. Do you see that? And as temperature increased, yield decreased. So as pressure increased, yield increased. As temperature increased, yield decreased. And this is what he noticed. And in summing it up, if a system at equilibrium is disturbed by a change in concentration, pressure, or temperature, the system will shift its equilibrium position so as to counter the effect of the disturbance. Okay? Everybody follow that all right? So let's see what that means. Okay, so here we've got an equilibrium between A plus B makes C. And at equilibrium, the concentration of A is 1, B is 2, and C is 5. So what is Kc? Well, we can fill that in, products over reactants, and it's 2.5, okay, or pretend one. But then some B is added to it. So now it's going to change. We're adding some B. What's that going to do to everything else? And we can use an erase box to figure this out. So now A is 1, B is 4, C is 5. Now, because now we got more B than we did. We did have 2, now we got 4. It's going to change according to the stoichiometry, minus X plus C. And then we add them up. But first, we need to decide, we really don't know about these positive and negatives first. We got to decide which way it's going so we can know, are these positive or negatives. So we put in our new values, 5, 1, and 4, and we get 1.25. 2.5 is bigger than 1.25, so our reaction is going to go this way, and that means this is plus, that's minus, that's minus. Everybody followed how I got that? I compared it here. Now, I can add them up, but we don't know these red numbers yet. We got to figure them out. So first of all, we're going to put in what we know to get, to solve for these concentrations we don't know at equilibrium. We know Kc is 2.5. We have our initial, we have our amounts here that we can fill in, products over reactants, and we can solve for X. But notice, you have to use the quadratic equation here. So make sure you know how to do the quadratic equation on your calculator before the AP test. If you have a TI-80, 2, 3, or 4, I can give you a program that you can use, or I can show you how to do it with graphing. If you have the 36, it can do it too, but you need to know how to use your calculator to solve for the quadratic equation. Make sure, because they'll probably give you a fancy one like this. So here we're going to solve, so we have to multiply 2.5 times these, multiply them together, and then multiply 2.5 for it. That goes on the other side. Gather up your terms, put a 0 on one side, put it into your program. That's the A term, B term, and C term, and you get 2 answers. But one of them will always be a nonsense answer. How do you know it's nonsense? It'll give you a negative number if you put it back in, and you can't have a negative concentration. So if we put back in 5, 4 minus 5 is negative 1, can't do it. So we know 0.04 is the right answer. We put it in, and then we can get our concentrations. So you see a little fancier way to do that. A little bit of fancy algebra there. So now we can put it in and fill in what is our new concentrations here by filling it in. And it's 0.6, 3.6, and 5.4 at our new equilibrium, now that we added more B. We changed it by adding extra concentration. And we have a little graph of what happened. It was at equilibrium, we added B, and it flattened back out again at our new concentrations. Notice they're all different now. All different new concentrations. Okay, I want to erase this. I want to see if y'all can figure these out.
Wait, can you go back up real quick?
Yep, I can. Do you need to go more than that?
Alright, I'm good.
You good? All right, let's see if y'all know these answers. You have a system at equilibrium. You add more reactants. Will it shift right or left?
Right.
Right, it will go toward the products. If you add more products, it will shift which way? Left, toward the reactants. If you remove reactants, remember, nature abhors the vacuum. It will try to fill that vacuum. Which way is it going to go? Left. And if you remove products, it will go right. is when there is a shift in the equilibrium position at constant temperature, will the value of K be changed? No. The only way to change the value of K is by changing the temperature. Now one thing you can do is change the pressure. Now, I taught this to honors, but I didn't teach it to them in the notes. I went back and added it later. And it's that pressure can affect it, and how it affects it is by the stoichiometry, by the number of moles. And it will shift to where there's less moles trying to fill the vacuum. So how this is written is this way. If you increase the pressure on a container by decreasing the volume, the equilibrium will shift to the side that has fewer moles of gas. And the opposite, if you decrease the pressure on the container by increasing the volume, it will shift to the opposite side, the one that has more moles of gas. Okay, do y'all remember that from honors? Okay, I didn't emphasize it very much. Okay, so here's a little picture. Notice this has got 2 moles, and that one has 2 moles, so this is not going to change it at all. Here are my frogs representing moles of gas. They're little gas frogs. But they both have the same, so that one's not going to change at all. Sometimes it doesn't. Okay, so here's another one. Suppose equilibrium has been established with 2 moles and 0.65 moles. The volume is reduced by half. So here is what it was, 2 and 0.65. But then it's reduced by half. And when it's reduced by half, it is going to double the concentrations. Okay? That makes sense. You got a container, you squish it down, it's going to be more concentrated, right? You just think about it. All right, so we can see here we were given what K was. It was 2.1. We were given Q, but I think I wrote that down wrong. I think it's 0.21. Let me see. Yes, I wrote it down. It's 0.21 and 4.2. So I wrote this wrong. That's what I get for writing it wrong. At least I noticed it. It goes that way. See, look, I copied it down wrong. KC is 0.21, so get rid of that little point. And so it is going to go to the left. There. When you copy the numbers down wrong, it can mess up your whole problem. Have to copy those numbers down carefully. All right, now it's right. So Q is bigger, it's going to go to the left. So that means that, did I write this down right? Plus. Yes, so we're adding this, we're subtracting that. So here are our concentrations, 4 and 1.3 are our new concentrations. This is what's going to happen. We can write our equations. Now we calculate what X is. We fill in our concentrations in KC. So we fill in our concentrations here, squared from that 2. The bottom one, not squared, from that 1. We're going to have to square that and use the quadratic equation. We get 2 answers, 0.18 and 1.2. 1.2 won't work because if you put it in here, it gives you a negative number. So that one's nope. And now this is the right answer. We can fill it in and get the answer. Does everybody see how we did that one? But they're all kind of the same, aren't they? Suppose that the pressure on the equilibrium system is increased by adding an inert gas. Is it going to affect it? No, because the ratio of the partial pressures will all stay the same. Okay, what about heat? If it is endothermic, you treat it as a reactant. If it's exothermic, you treat it as a product. So if it's equilibrium and it gets hotter, then if it is going to be like it's a reactant, if it's endothermic, and products if it's exothermic. If you decrease the temperature, then you're going to treat it like it's a reactant for an endothermic and a product for exothermic. And whatever would happen with that product or reactant, increasing it or decreasing, that's what's going to happen. That'll make more sense when you do a few problems. But all you'll have to do is, oh yeah, I just treat it like a reactant or a product. So here's a little chart summing that up. It will shift right. If you add heat and it's endothermic, K will increase. It'll shift left. If it's exothermic, K will decrease. If you remove heat, you cool it off, it's endothermic, it'll go left. The value of K will go down. And if it'll go right, it'll go up if it's exothermic. Okay, last page. Okay, you may recall that increasing the temperature of ammonia reaction mixture caused the percent yield for it to decrease. Considering that, then it would be exothermic. If you go back and look at that, you would see that. Okay, there's our little table. Now, so a catalyst lowers the activation energy barrier. This affects the activation energy for forward and reverse. Therefore, adding a catalyst to an equilibrium system will have what effect on the value of K? None. It only affects that energy of activation. But if you add a catalyst, what happens is that the thing will reach equilibrium faster. Do you see that? So this one has a catalyst, that one does not have a catalyst. They both get to equilibrium, but the one with the equilibrium gets there faster. So does it change the equilibrium? No, you just get there faster. So what happens is the rate at which the equilibrium is achieved is faster. Okay, that's the notes. How do you feel about that section? All right, like, share, subscribe.